So my name is Norbert. I work at the Austrian Institute of Technology, and now the slide appears. Thank you for inviting me to this workshop. It's a challenge to be in the last session in terms of level of attention, but also an opportunity maybe to refer to some issues which arose yesterday and today. So the Austrian Institute of Technology is a sort of hybrid organization. We are a non-university research institute, but we have also a rather pressure to produce solutions at a relatively high TRL, technological readiness level. And on the other hand, we must also produce academic excellence and results. And my talk will cover both aspects, and I chose to dive into a special topic about the mobility data collected from smartphones. A thing we all have in our pockets now. We saw it several times today. There are many sensors in it, and you can compute mobility data out of it. So the first thing, the first part about of the talk is the concept of the smartphone-based travel survey in general, and then I take the opportunity to make a little promotion about our stuff. This is at a very high level, the division between you have an app collecting sensor data, and at some point in time it collects this sensor data to a server. You have a server doing smart analysis, maybe inferring travel modes, and you have a storage. And for the classical survey setting, you have interpreted data and the respondents doing some trip validation if you do a classical mobility survey, because this increases the trust because the users look at it and confirm it. So we had three ways yesterday: the American way, the European way, and the Chinese way. The American way is Google. Google does a lot of this stuff. It already collects these data. If you look at Google Maps at locations, you see popular times, less popular times. If you subscribe to it, you can have a look at it. At your own travel modes, you can correct it and provide them with training data. You can even annotate horseback riding, so very strange travel modes. The thing is, it is Google, and we don't trust it, referring to the topic of this workshop. So I will leave out the Chinese way. We have a solution doing it the European way, and often people going around and selling systems, like in IoT, they say we have European or German data protection standards, and that is also something we put the focus on. We have another, the solution is called Smart Survey. I will show you some screenshots afterwards. One aspect of trust is also here. We had some guy trying to break into the system in every possible way and to hijack it, and we got rid of these errors, and now we have a certification, so it's the TÜV. So this also increases the trust, what happens with the data if they are transferred. So basically these three components. The most informative sensor, it's already mentioned several times, is the accelerometer, which measures the forces on the smartphone. It's also very cheap to read out in terms of energy. And there are other sensors like gyroscope, barometer, and other stuff as well. But in many solutions, it turned out that this is the most informative one. So in terms of the concept, we developed a solution to be ready applied in surveys. So the organizer distributes anonymous IDs. We are the technology provider. We do not know the contact data or the phone data. Might be a QR code just to read in. The app is installed. It's an Android or for iOS. We have both solutions. Several markets. In Switzerland, for example, iOS has a very high distribution. And the user just chooses a user ID and a password. And also very important, the user agrees to a privacy agreement. Now GDPR compliant, you explain why it is being tracked and what is the purpose of it. You want to infer the travel modes. And Our concept is the app runs in the background, so the user is not bothered with any questions. The principle is to be really ambient, so you have it in your pocket and the data are collected. And GPS is only collected during trips, means if you're outside, because GPS is notoriously intensive on battery power. So we have seen many screenshots so far. This from Slovenia guy who tracks himself. I tracked myself. This is just one sample away from home to work. And here, here's the equivalent of a mobility diary. You have the walking stage, subway, pedestrian, train. You've seen it before. And the thing is, I heard before, I thought it was walking, cycling, and driving. Our solution covers 8 different travel modes, and you see here at the top the menu where you can choose several stuff. One of the most important thing, of course, is the mode of transport. You can look at the modal share in terms of train, tramway, subway, bus, car. So very similar means of transport. I mean, walking and cycling are quite different, but distinguishing a car from a bus might have some challenges. You have tokens for the end user, for the respondents, but you have also tokens for the survey or organizer who can monitor the progress. So how many trips have been uploaded in average, how active are the user. It's also possible to monitor certain IDs which maybe did not upload for 2 days, they can be contacted. But again, the thing is, it runs currently at AIT, and we do not have any knowledge about the identity. So, of course, the organizer has to prefer some first level support. So I do not see any trips. So then we say you need to have a data connection, and this must be covered by the survey organizers. The classical questionnaire is also built into the system. Currently, it is according to an Austrian standard, where there are some household-related questions. The whole survey is household. The concept has the concept of a household, and of course, you can see here typical statistics about the distribution, socio-demographics. This can be adapted if we implement a new instance of a survey. And again, some nice heat map as well. Where are really the trips which have been covered. This is an example from 2 regions of Austria where we did a sample survey for another application, which is the electronic ticketing, which is very popular. Public transport operators are keen on, well, people do not have to mess with apps or kiosk or anymore, but it's really ambient computing by the smartphone. So ideally, public transport trips are detected, the start and the end. There might be several trips on the day, and at the next morning, the public transport operator computes the cheapest option. So this is a very hot topic, and this was a sample survey conducted with 500 volunteers, so real people, and the Austrian Railways conducted these surveys and provided the first level support. One thing concerning, now I have a city, another region, can this be applied immediately? And the answer is, it depends on the characteristics. My example is it fits well to the city of Lisbon. We have seen already here nice pictures in the morning. I had a city break at the more modern part of the expo area, and you see here 2 phenomena, straight lines, not really nice routes. This is, of course, you go there by subway. You don't have any GPS information. The route information cannot be properly displayed if you rely on GPS alone. And interestingly, there is a bicycle route on the water. And this is because, well, you have the cable car. It is currently not really considered in our set of travel modes, and it's wrongly classified here. Of course, You have a speed similar to the bicycle and maybe up and down forces as well. So the decision is to classify it as a bicycle. And the other thing is covering the underground stuff. We do multimodal routing or routing, what the Americans say. You have regions which are not covered by GPS, so we have in-house router closing the gaps between endpoints and thus providing seamless routes. So here is the example where I change my travel mode. It's completely underground, but still what the system provides is a seamless and a nice visualization of that stuff. So this was a quick view on our solution. It was more the promotional stuff. Now I go into I would say the core topic of this workshop. When I was thinking about what could I tell about it, and it's more the scientific stuff. So what is it now about the accuracy? So we heard yesterday we have a solution providing to some level of accuracy, a certain level of accuracy, but it's not really known. But it's very important to know that level of accuracy because there are many applications who want to decide if there is a significant change, for example. We applied this system for a commuter parking pricing, a new pricing scheme also with real commuters, and the idea was to reward them if they use public transport. So now for the modelers on top of the application, if they perceive 5% change, they want to know is it within the error or not. So there should be some figure provided out of this travel mode calculation, and we should know, can we trust it? So that's the topic of the trust. Travel mode classification itself, to go more towards academia. I think every month a new paper appears about a new method of travel mode classification. And of course, many boast about 95%, often it is about above 90%. The question is, it's often, or most of the time, it's not really clear how they did evaluate their results. Sometimes it's just a few students running around and for a few days capturing their stuff. Sometimes other people annotate and find out or figure what could have been the real route. So they are not specific about the evaluation procedure. And the question is then, what do I have? I have different numbers. Can I compare it, or is it really comparing apples and oranges? Is there a way to do that? So the typical approach for evaluation is, so we are now into machine learning. Training data are collected from people with sensors, and you have labels. And you have a set of data collected, and now you want to do the core task of machine learning, provide a machinery which is ready for the future, for unseen data. So what you do, what you have collected is you split it randomly. You have here the lottery into a set of training data and a set of evaluation data. So you train your predictor on the training data, and afterwards you evaluate it on the test data. Then you can compute accuracy, precision is often used, how accurate is this, but also the recall, is every travel mode recognized, and the F1 score, which is a nice combination of precision and recall, because melting it down to one figure is always quite nice. So if you have, we had it yesterday, patches of cars maybe, or satellite images, you have 100,000 of examples, then you leave 10,000 out, train it on the 90,000, and then you find out what happens on the other. That's the usual way of splitting it. What you want to do if you do that, if you develop this machine learning, what you have to do really in a city, you have to collect an unbiased sample. And this is already quite difficult. We had in our first study, the test data were collected from students of the University of Natural Science. So they were more biased towards bicycle, students. Car usage was underrepresented. So it does not, and if you do not have cars well represented in the data, it will fail for the travel mode in the future. So it should be really a sample of the target distribution. The problem is it's a complex and moving target. If you really critically view it, car sharing systems are introduced, which may invoke a behavior shift from public transport to car transport, maybe unintended, or bike sharing systems are introduced. They're constantly changing data in a city, what you collect. And the question is, so can a subset really ever be truly independent if you collect such a thing? And you have take into account, you have, let's say, accelerometer signal, maybe some other signals, but what is really going into that, if you carry a smartphone, it's the person, every person have an individual driving style, a gait, which means a walking pattern. The travel route, somewhere you have a pavement, some on the other location you have some other underground which will produce vibrations. The traffic state, if it's more congested, stop and go traffic will have an influence. The type of vehicle, we learned that we can pretty much distinguish public buses because of the diesel motor producing very, these high frequencies. But if you have an electric bus, this will be gone. So, position of the device, it depends if it's in a pocket, in your backpack, in a bag, in the hand, in the smartphone holder. Then, of course, people do not have their smartphone in the pocket. Maybe you look, if you ride public transport, people use their phone, they browse the internet. So the device is constantly moving. And sitting, walking, standing in public transport, you go on the train, into the train restaurant. So it is really, really complex. But what you want to do to find out all of this is the travel mode. So you have a really huge variety of influence factors, and the question is, will it ever be possible to cover this wide variety and to avoid the correlations, to avoid that it is learned towards a single person and it will not work for another person. So the evaluation results will strongly depend on the characteristics of the data. If you only collect car travel, it will be good detecting car travel. If you underrepresent bicycles, it will be bad then for detecting bicycles. And the states so far, as compared to other machine learning tasks like face detection, pedestrian detection, car detection, whatever is, so far it's very hard to compare the results because there is not really a data set for benchmarking, and that is the proposition that we made last year. So to carefully collect and publicly available to make an evaluation data set. What happened last year? There was a challenge. Now such a data set is released. You see this guy, he's not completely happy because he has to wear 4 smartphones and he collected for several hundred hours the data, which is not the problem. The hard task is to label it and to correctly segment it. So retrospectively, he annotated the data and provided this so-called ground truth. And this was the SHL Challenge in Singapore. And this is the result of the competition, which reveals quite an awful truth. You see in red is what people reported on their training data, and the test data, the labels were not released, and except 4 contributions are in the same area about in the training and test set, and the other ones strongly go below towards even 50%, which means random. So this means machine learning skills alone may be not sufficient. I just want to make 4th position is our contribution from our group. What we found out is first we did it as everybody did, randomly split it. What we found out is there are high correlation between the frames. What is evaluated are 1 minute frames of data. And even after 20 minutes, there is a 25% correlation of the data. So what we did was to order them temporarily. You just take a step of training data and then the test data, and then the result drops from 95% to 83%, which is not as good as before, but better predicts the unseen training data. It worked even better for segments where in 1 minute the transportation mode changed. So if you see in yellow, the first 3 places are really did not tackle that problem. And it's also classification, that's my last slide. In addition to classification, segmentation must be solved and properly compared. And the take-home message is the performance figure achieved in the lab, what we call it, must be really read with caution. The respondents can confirm the trip. This can be used for the statistics, but not for ground truth, because if you provide them with incentives, confirm at least 60 trips, then some people might just click through to get their vouchers, their Amazon vouchers. So more comprehensive benchmark data sets are needed. And in terms of machine learning, we are constantly improving the methods, combining trip purposes to increase the robustness, also against errors in the map data, which are prevalent as well. So this concludes my talk, and I'm happy to answer any questions.